Greetings everyone, welcome to Side A, Side B. In this video, a discussion on how the periodic functions are derived from the unit circle. The overall plan begin with the basics of trigonometry. So, what's in our toolbox? How about what we know from proportion and the Pythagorean theorem? First, a discussion on the basics of trigonometry and see where we can go from there. Overall, consider our study of trigonometry as a work in progress. First, cosine and sine are functions in terms of ratios, set up in order to solve angles such as the yellow curve. This type of approach to solve angles only works for right triangles noted with the square yellow. First, notice cosine equals the adjacent side over the hypotenuse h. Then, just imagine holding a triangle, your eye level, in the direction of the line PQ. It's tempting to consider side H as the adjacent side, but H is always the opposite the right angle. The adjacent side, follow the blue arrow. Does that make sense? Next, notice sine equals the opposite side over side H. Your eye level is still in the direction of the line PQ. The opposite side is appropriately opposite of the yellow curve. Follow the orange arrow. See that? Let's try to back engineer, sort of, to understand the origins of cosine and sine, the line of thought. By considering the following similar triangles, we know by Thales' theorem we can inscribe the smaller triangle inside the larger one so that line F is parallel with line A. For similarity to hold between any two triangles, just two conditions are needed. All of their corresponding angles equal each other, and their sides are proportional. For sine, we have the ratio equality 1. We multiply each side by b and divide each side by k to get equation 2. Opposite over hypotenuse equals the same. See that? We can do the same for cosine if we move the smaller triangle in such a way that line G is parallel with line B. See where this is going? The human analytical mind noticed we can make a function derived from the relationship between the ratio of sides and angle, such that since we can find any larger or smaller similar triangle than the original triangle, the relationship will always hold. It follows the relation is transposed as a left and right-hand side equation set up to solve for any angle for a right triangle. That being said, rearranging the blackboard, it follows if we want to find angle P, then because of the relation between the angle and the ratios, it's set up the following way. Cosine of P equals A over C, and sine of P equals B over C. Now hold the triangle so your view is in the direction of the line QP. To find angle W, the adjacent and opposite sides switch. Then cosine of W equals B over C, and sine of W equals A over C. The first thing we thought of when we learned about trigonometry, if sides A and B don't equal each other, then their ratios will return a different value, implies a different angle. True enough. However, when we solve for angle P, we actually take the inverse of cosine and sine, which will return the same angle. Nice. But that's for another video. For now, exploring the relationship of the Pythagorean formula and the unit circle and what that returns. As it were, exploring the possibilities of a relationship. Let's begin. Welcome back. We're given the assignment exploring the possibilities of a relationship. Okay, sounds good. Then, first, let's make use of what we know about distance, letting A equal 1 and B equal 0, then solve for C in the blue box. Next, let the yellow ray equal length 1, Then rotate it such that it makes a circle with radius 1. Voila! The unit circle. Going counterclockwise in the red, we have points A equals 1, B equals 0. Then all the rest of the pairs. 0, 1, negative 1, 0, then 0, negative 1, finally back to where we started. Now imagine a yellow curve that terminates at the orange line, which makes an angle theta blue. Nice. Immediately after, let's combine everything so that we inscribe a right triangle inside the unit circle. Everyone, put down your phones for one moment. Take a look. It follows. The hypotenuse equals 1. See that? Everything else naturally follows, like angle theta blue. Adding the details, such as side A is entirely on the x-axis, and side B corresponds to the y-axis. The red point is the pair A and B. Now the diagram should start to look very familiar. Since the hypotenuse C equals 1, we can rewrite the Pythagorean theorem as a squared plus b squared equals 1. Recall, the cosine of any angle equals adjacent over hypotenuse, and sine theta equals opposite over hypotenuse. Then, let's make the appropriate substitutions to get cos theta equals a over 1, which just equals a, and sine theta equals b over 1, which just equals b. Very nice. But why is that so darn beautiful, you might ask? Because we can rewrite the white box again to get the blue box. We have cos squared theta plus sine squared theta equals 1. Notice we typically write the square as follows, like it's applied to cosine and sine instead of the angle, which could look familiar to some because the blue box is called the Pythagorean identity, which we want to prove in another video. Knowing what we know, the red point is now the pair cosine and sine. Let's repeat what we just did, going in a counterclockwise direction, but this time let's plot cosine on a graph with the red points. We have cosine equals 1, 0, negative 1, 0, then back to the original point. Do a repeat, in a counterclockwise direction, but this time let's plot sine on a graph with the red points. We have sine equals 0, 1, 0, negative 1, then back to the original point. So what did the relationship between the Pythagorean formula and the unit circle return? If it's not obvious, points on a graph, which could lead to plotting two periodic waves, plus a bonus identity. Not bad. On that note, the potential to finish this discussion for another video. The relationship between an end to an end is an end. Until next video, ladies and gentlemen. Agoda. That's what you should put, man. That's you, because that's you.